Hello, I'm Ali. In this video, I'll walk you through the process of repairing structural parts directly on site. With 15 years of experience in engineering, maintenance, business development, and project management, I've been at the forefront of driving innovation and growth in the energy industry. We will explore the processes, highlight both the benefits and risks, and discuss the critical steps required to repair the structural parts. On-site repairs play a pivotal role in minimizing downtime and reducing costs while allowing for customized solutions tailored to specific operating conditions. By following a structured approach, we can ensure that even the most complex repairs are handled efficiently and effectively. Whether it's patch, fabrication, material rejuvenation, or the final inspections, every step is crucial to restoring the integrity and functionality of these vital components. Much of my work in on-site repairs has involved Siemens models like the SGT 2000E series, as well as Alstom engines, which are now under GE's care. In this video, we'll explore various aspects of these repairs. The benefits are: by repairing components on site, you eliminate the lengthy process of shipping parts to and from a repair facility. Parts can be repaired and reinstalled quickly, minimizing the turbine's downtime. Avoiding the shipping of large and heavy turbine components reduces costs significantly. On-site repairs often require fewer specialized personnel compared to full-scale repair facilities. On-site repairs can be tailored to the specific operating conditions of the turbine, ensuring that adjustments are made to optimize performance. Additionally, coordinating an on-site repair is often simpler than managing the transport and scheduling of components at an external facility. Plant operators can directly oversee the repair process, ensuring that the work meets their standards and requirements. The risks include the potential lack of access to specialized tools and equipment that are typically available at dedicated repair facilities. Additionally, space limitations on site could restrict the ability to carry out complex or extensive repairs. The quality of on-site repairs might not match that of a controlled environment in a repair facility. Advanced diagnostic tools for in-depth inspections might be limited on-site. On-site repairs can be affected by weather, temperature, and other environmental conditions. Highly specialized personnel might not always be available on site, leading to potential gaps in expertise. For severe damage or complex repairs, it may be impractical or impossible to conduct the necessary work on site, necessitating transportation to a specialized facility anyway. For advanced gas turbine versions with specialized coatings, the repair process becomes significantly more challenging. In this example of the Siemens SGT 2000E series after disassembly, structural parts like flame tubes, inner casings, and the combustion chamber will be inspected at the site. After performing a visual inspection, which identifies visible cracks, corrosion, or other surface anomalies, a trained inspector examines the parts using tools like magnifying glasses, borescopes, or even just the naked eye, often supplemented with lighting or other aids. Several other non-destructive testing methods can be performed on-site to check for cracks and corrosion on gas turbine parts. Here are some common ones. In ultrasonic testing, high-frequency sound waves are transmitted into the material. The sound waves reflect off any internal discontinuities, and the reflections are analyzed to determine the presence and size of defects. In magnetic particle inspection, the part is magnetized and iron particles are applied to the surface. If there is a crack, the magnetic field will be disrupted, causing the particles to gather at the discontinuity, making it visible. In eddy current testing, an alternating current is passed through a coil, generating a magnetic field. When the coil is placed near a conductive surface, it induces eddy currents. Discontinuities in the material, such as cracks or corrosion, disturb these currents, which can be detected and analyzed. In radiographic testing, X-rays or gamma rays are used to penetrate the material. The rays are absorbed differently by different parts of the material, and any internal defects are revealed on the radiographic film or digital detector. In acoustic emission testing, sensors are placed on the surface to detect the high-frequency sound waves produced by cracks or corrosion as they develop and grow. Fluorescent penetrant inspection is another non-destructive testing method used to detect surface breaking defects in non-porous materials by applying a fluorescent dye, which highlights cracks and flaws under ultraviolet light. It's widely used for inspecting critical components. If required, a test piece will be sent to a lab. Perform dimensional verification according to the design specifications. Based on the extent of the damage, follow the outlined repair scope. Typically, the process involves the following steps. When addressing the repair of structural parts on site, follow the outlined scope based on the extent of the damage. The typical process involves the following steps. Ensure you have the appropriate reinforcement tools for the machines you're working with, along with the general tools required for the job. Fabricate new patches with the required surface area to cover the damaged section. Straighten the part to restore it to its original shape, ensuring it aligns with design specifications. Conduct a dimensional inspection to verify all components meet design specifications. Accurately position and secure all necessary fixtures before proceeding with further treatment. Perform heat treatment to rejuvenate the base material and restore its properties. We performed this in a locally manufactured insulated bunker. Imagine large steel insulated structures similar to oversized Lego pieces. These bunkers are engineered to achieve specific temperatures based on the selected burners. The model shown can reach temperatures up to 2000 degrees Fahrenheit. While it's an investment, the reduction in downtime and repair costs over time offsets the initial expenditure. Remove all fixtures post-heat treatment. If required, carry out a metallurgical analysis to assess the material's condition post-rejuvenation by sending test samples to the lab. Clean the surface by grit blasting to prepare it for further inspection and repair. Set up a temporary grit blasting area at a safe area at the site. We will cover key steps from site preparation to breakdown, ensuring safety, efficiency, and compliance to perform grit blasting at the site. First, select an appropriate location for the temporary grit blasting area. Ensure the site is well ventilated and positioned away from sensitive equipment and personnel. Install protective barriers or containment to prevent grit from spreading to nearby areas. This helps maintain a controlled environment. Safety is a top priority. Ensure that all personnel involved are equipped with proper PPE, including respirators, gloves, and protective eyewear. Post-clear signage, such as grit blasting in progress, around the work area to alert others. Regularly monitor the air quality and use dust suppression systems to maintain a safe working environment. Position the grit blasting equipment in the designated area and check that all tools are functioning correctly. Confirm there's adequate power and air supply for continuous blasting operations. Set up grit collection and recycling systems to minimize waste and optimize resource use. Inspect the components before blasting. Make sure they are clean and free from oil or grease. Mask off or cover any areas of the components that do not require blasting to protect sensitive surfaces. Begin blasting, maintaining a consistent distance and angle to ensure even material removal across the surface. Regularly monitor the grit material and adjust the blasting settings as necessary to achieve optimal results. After blasting, remove any residual grit from the components. Carefully inspect the components to ensure the desired surface finish and cleanliness have been achieved. Dispose of or recycle spent grit materials following the appropriate protocols. Once the process is complete, clean the work area thoroughly, ensuring no grit or debris is left behind. Safely store or dismantle the blasting equipment as required. Finally, restore the area to its original condition, ensuring there is no environmental contamination or safety hazards left. Use dye penetrant inspection or other NDT methods to detect any surface flaws. Address any issues such as erosion, cracks, and fretting. Remove any damaged material, including bulge sections, heavily cracked areas, or burnt material. Weld new patches onto the part as needed. Conduct a post-welding dimensional inspection to ensure accuracy. Reposition and secure fixtures for stress-relieving heat treatment. Perform stress relief heat treatment to stabilize the structure. Remove all fixtures and perform a final grit blasting to clean the surface. Carry out a final round of dimensional and dye penetrant inspections using 100% dye penetrant tests. Complete the final inspection to confirm that all repairs meet the required standards. Document the entire process, certify the repairs, and generate a comprehensive report. While on-site repairs offer numerous advantages, there are some limitations. Despite these challenges, on-site repairs remain a valuable option for many situations, saving both time and money. Thank you for your time. I'm happy to answer any questions you may have, and feel free to contact me if you need further information.